Every modern AI breakthrough seems almost magical, right? I mean, we're seeing models that can instantly write thousands of lines of perfectly functional software code. Artificial intelligence predicting three-dimensional protein structures to help cure diseases in a matter of seconds. And chatbots capable of holding fluid, incredibly nuanced human conversations. But behind nearly every single one of these world-changing breakthroughs is one specific company. And for decades, most people only knew them from making graphics cards for video games. Well, welcome to this explainer, where we are going to unpack the story of the foundation of the modern machine age. We're looking at exactly how a company founded to render pixels on a screen quietly became one of the most important, valuable, and globally powerful entities on Earth.
Okay, let's dive into this. To really grasp the AI revolution, we first have to understand the massive, almost mind-blowing contradiction at the very heart of the company powering it. For a long time, NVIDIA's primary market was, Mountain Dew field teenagers and PC enthusiasts lugging their computers to LAN parties, people who just wanted their video games to look as realistic as humanly possible. They built hardware specifically to render cool explosions in Quake, dynamic lighting effects, and incredibly fast-paced graphics. Yet today, this exact same fundamental technology is the engine driving global AI research. It's the hardware sitting in sterile, highly secure data centers run by PhD research scientists who are training trillion-parameter models. So how on earth do you get from a video game explosion in the 1990s to a global artificial intelligence revolution today?
So, the answer actually lies in the fundamental architecture of computing. Most computers rely on a CPU, or a central processing unit. Think of a CPU like one incredibly fast, highly intelligent master chef in a kitchen. They can cook absolutely any complex recipe you give them, but they have to do it sequentially, one step at a time, one dish at a time. NVIDIA, however, makes GPUs, or graphics processing units. If a CPU is your one master chef, a GPU is, well, actually scratch that. It's more like an army of 10,000 fast food cooks. Individually, they might not be as universally capable or highly trained, but if you need to flip 10,000 burgers at the exact same millisecond, they can absolutely do it. In graphics, you need to calculate the color of millions of individual pixels simultaneously on a screen. That requires what we call parallel processing. And as it turns out, artificial intelligence learning is fundamentally just massive matrix multiplication. It requires solving millions of tiny, simple math problems at the exact same time just to recognize patterns in data. In short, AI needs the burger flippers.
Tracing this whole evolution back to 1993, founders Jensen Huang, Chris Malachowski, and Curtis Preem started NVIDIA to capitalize on the early PC gaming market. And let me tell you, the 1990s graphics card market was literally a bloodbath. It was an era of fierce, brutal competition where dozens of promising hardware companies completely disappeared or were bought out for pennies. NVIDIA managed to survive this gauntlet, totally solidifying their place in the gaming world. But behind their eventual astronomical success in the modern era was one extremely risky strategic decision they made years later in 2006. It was a move that, at the time, seemed like a massive gamble, but it ultimately changed the entire trajectory of human computing.
Section 1. The decision that changed everything. However, almost nobody knows this part of the story.
While everyone else was entirely focused on making video games look better, NVIDIA's leadership had this major realization. They realized that their parallel processing chips could theoretically be used for something far, far beyond gaming. They saw that scientists, researchers, and engineers could use all those thousands of simultaneous calculations to solve really complex mathematical problems, but there was a massive hurdle. To do that, researchers needed a way to actually program the GPU, which at the time was notoriously difficult and required highly specialized graphics knowledge. So the absolute crucial point is what they built next: CUDA. Released in 2006, CUDA was a software platform that allowed developers to use NVIDIA GPUs for general-purpose computing. Suddenly, you could be a climate scientist running weather simulations or an AI researcher testing neural networks. The financial risk here was immense. NVIDIA invested heavily in this software platform, literally pouring billions of dollars into it and essentially subsidizing it for years. Wall Street thought they were crazy for spending so much capital on a scientific computing market that barely even existed yet. But leadership firmly believed that if they built the tools, the scientific community would eventually adopt their chips.
And that long-term, high-risk bet, it famously paid off in 2012 with the ImageNet breakthrough. Researchers created a neural network called AlexNet to compete in a prestigious image recognition competition. But instead of training their AI on standard CPUs like everyone else, they used NVIDIA gaming GPUs programmed via that CUDA software. The results were staggering. What would have taken standard processors weeks or even months to calculate, These gaming chips accomplished in just a few days. AlexNet absolutely crushed the competition, demonstrating a level of machine learning accuracy that completely shocked the computer science world. This was the spark. Almost overnight, the entire AI industry woke up and realized that GPUs were the secret key to deep learning. One massive investment in software years earlier completely reshaped the future of technology.
Section 2. Building the AI infrastructure. Now, what's really interesting about this is how AI is actually built today.
Because look, we've moved far beyond a few researchers just plugging a graphics card into a desktop computer. To build the artificial intelligence we interact with today, you need infrastructure on an almost unimaginable scale. Modern AI is trained in massive data centers, often spanning the size of multiple football fields. Inside it is a physical reality of deafening industrial cooling fans and endless racks of servers. You don't just have one or two chips, you have tens of thousands of clustered GPU accelerators all linked together. These massive supercomputers ingest the petabytes of data required to train foundation models. And to do this without any bottlenecks, scaling compute really matters. It requires incredibly high-speed networking and literally miles upon miles of specialized fiber optic cables to keep all those thousands of GPUs fed with data simultaneously.
And this brings us to why NVIDIA is so deeply entrenched. They don't just sell individual chips anymore, they sell a whole shebang. It's an entire, inescapable AI computing ecosystem. They design the AI accelerators, the high-speed networking that connects them, the software that runs them, and the platforms used for AI inference. What they have built is an incredibly deep technological moat. Because developers learn to code AI using CUDA, and CUDA only runs natively on NVIDIA silicon, developers are essentially locked in. By integrating deeply with cloud computing giants, NVIDIA has ensured that if you want to build serious AI right now, you are almost certainly living entirely within their ecosystem.
Section 3. The numbers behind the dominance. And this brilliantly illustrates exactly what happens when you hold the keys to a technological revolution.
We are currently witnessing unprecedented research and development, alongside massive capital investment in AI semiconductors globally. Big tech companies, well-funded startups, and entire nations are pouring billions upon billions of dollars into securing computing power. It is quite literally a modern technological gold rush, and the pickaxes everyone is rushing to buy are GPUs. Just to put this spending into perspective, we're talking about single tech giants ordering hundreds of thousands of these chips, and these chips cost upwards of $30,000 or $40,000 each. The capital expenditure is just mind-boggling. That's enough money to fund entire nations, just being poured into silicon. The demand for these advanced chips has outpaced almost any hardware rollout in the history of computing.
The dominance here is absolute. When it comes to the specific chips used to train advanced AI models in data centers, NVIDIA commands the vast majority of the global market share, leaving all their competitors fighting for just a tiny fraction of the space. Even technological titans like Google, Amazon, and Microsoft, who are frantically trying to design their own custom in-house AI silicon to break free from this dependency, they still have to buy tens of billions of dollars worth of NVIDIA hardware just to stay competitive in the current AI race. Simply put, nobody can afford to wait for an alternative.
This massive tectonic shift is captured perfectly in their revenue. For decades, gaming was the undisputed king of NVIDIA's balance sheet. It was their entire identity. But in recent years, data center revenue has just exploded, completely eclipsing their original core business. This shift isn't just a financial metric, it's the visual proof of a company's total metamorphosis. Look at the sheer scale of this turnaround. They're no longer a gaming company that happens to do AI. They are the central pillar of global AI infrastructure that just also happens to make gaming cards on the side.
Section 4. Geopolitics and global dominance. The real reason this matters is actually a lot more complicated than just corporate revenue.
When technology becomes this critical to the future of the global economy, it completely stops being merely a consumer product and steps right onto the global geopolitical stage. These chips are now universally recognized as critical national strategic assets. Governments around the world have developed national AI strategies, basically knowing that whoever controls artificial intelligence will likely control the economic and military future. And this introduces a massive geopolitical choke point. You see, these highly advanced GPUs are designed in California, but they rely on incredibly complex fabrication that is primarily done in Taiwan by TSMC. This highly concentrated, deeply fragile global supply chain makes access to raw computing power a literal matter of national security and global superpower supremacy.
Section 5. The hidden challenges. Let's take an objective, balanced look at the entire landscape here, because it's definitely not all smooth sailing.
Of course, holding this much influence in an emerging, resource-heavy industry doesn't come with significant friction. When we weigh the opportunities against the risks, a highly complex picture emerges. On one hand, the technological opportunities are just staggering. We're talking about accelerating quantum computing research, powering autonomous robotics, and significantly slashing the time it takes for pharmaceutical drug development. But the physical risks and limitations are equally massive. Geopolitical tensions have led to strict export controls, heavily restricting where these powerful chips can even be sold. Then there is the physical reality of energy consumption. These modern GPU clusters draw so much electricity that major tech companies are now literally looking into purchasing dedicated nuclear power plants just to keep their AI data centers running without crashing local power grids. Adding global chip shortages, raw material dependencies, and concerns about AI monopolization, and you can really see how fragile this global reliance truly is.
Section 6. The Future of Computing. Let's move to and see how this builds toward the decades of 2030, 2040, and 2050.
Because despite the physical and geopolitical challenges we just talked about, the roadmap for the next generation of computing is already being drawn up as we speak. Grounded in current industry trends, the next era of infrastructure will scale far, far beyond the chatbots we use today. We're looking at a future defined by massive AI supercomputers dedicated entirely to scientific discovery. One of the most fascinating developments is the implementation of digital twins. This involves using massive GPU compute to create a one-to-one, real-time virtual simulation of an entire real-world city's traffic grid or even a complex global supply chain, allowing us to accurately predict physical failures before they even happen. Along with reliable autonomous vehicles, edge AI, and entirely automated smart factories, none of this is science fiction. It is the direct application of scaling the parallel computing ecosystems that are currently in production right now.
And this really brings our story full circle. It is incredibly important to remember that NVIDIA didn't invent artificial intelligence. The concepts of neural networks and machine learning have been around in academic papers for well over half a century. But history often remembers the inventors who stand in the spotlight while overlooking the builders who create the foundation. In the age of artificial intelligence, by sticking to their core technology and making one brilliant, highly criticized software bet years before the market ever caught on, NVIDIA built the tools that made today's AI revolution physically possible. They became that foundation.
The world is changing rapidly, and now you understand exactly why and how the infrastructure of this new era was laid down. But it leaves us with a fascinating and honestly somewhat daunting thought to ponder as we look to the future. If nearly every major AI breakthrough, every geopolitical technology race, and every roadmap for the future of computing runs through a single ecosystem, what happens when the next chapter of human innovation depends entirely on what one company builds next?
Thanks for watching World Decoded. Make sure to like and share, subscribe, and stay curious.